Hey, hello everybody. My name is Liam Jordon and I am a PhD student in Maynooth University in Ireland. And today I would like to present a talk based on work done alongside my supervisor Philippe Moser titled Normal Sequences with Non-Maximal Automatic Complexity. So again, today we're going to discuss automatic complexity. We'll discuss what it means for a sequence to be normal, and de Bruijn strings are going to pop up time and time again. So just so we're all on the same page, a string is going to be a finite concatenation of zeros and ones. So we're mainly just going to deal with the binary alphabet in this talk. A sequence is going to be an infinite concatenation of zeros and ones. So a string of zeros and ones going on forever. And then if we see this notation here for a sequence, or for a string for that matter, s and this square brackets 0 dot dot n, this just means the prefix of s of length n plus 1. So take the first n plus 1 bits of s. And again, I assume everyone here is going to be familiar with DFAs. Okay, so what is automatic complexity? Well, it's a finite state-based complexity notion that was introduced by Shalit and Wang in 2001. And essentially, it's a distinguishing complexity for DFAs. So to be specific, the automatic complexity of a string x of length n, and we denote this by a of x. This is the smallest number of states required by any DFA M, such that x is the only string of length n that M accepts. So in a sense, M is able to distinguish x from all of the strings of the same length as x. So in essence, we're looking for the smallest DFA in terms of the number of states that does this. If the input has length different to the length of x, we don't really care what happens. We can accept or reject. However, if the input has length equal to the length of x, we only accept if the input actually is x. Otherwise, we reject. So this is what we're looking for. So a very simple example, if we're dealing with the binary alphabet, any string composed of just zeros has an automatic complexity of 2. And this can be witnessed by this DFA here, because very clearly, as you can see, the only string of length 3, for example, that's accepted by this DFA is the string of 3 zeros. The only string of length 2 that's accepted is the string of 2 zeros, and so on. Something else that's pretty clear straight away is that every string x has an automatic complexity bounded above by its length plus 1. So say, for example, x had length m. We can easily build a DFA such that x is the only string of its length that's accepted by for each state, for each character in x, we can just read it bit by bit, traversing through a state for each bit, and then upon reading the last character of x, traversing back to the start state and having that be an accepting state. And at any stage, if we see something we don't expect, so we see a 0 when we expect to read a 1, we'll just traverse to this fail state, or this dead state over here. Okay. So again, we're going to be looking at sequences in this talk as opposed to strings, but you can't input a sequence into a DFA, and we can only input strings. So instead, what we will be looking at is this ratio here. So for sequence T, we're going to be looking at the automatic complexity of prefixes of T divided by the length of that prefix. And this is the ratio we're going to look at. So for the upper automatic complexity ratio, we will take the lim sup of the ratio here. And for the lower automatic complexity ratio, we just take the lim inf. So this could be essentially seen on this diagram here. If these two blue dots are the ratios, essentially we're looking for what's the value of the lim sup and what's the value of the lim inf as we take longer and longer prefixes. So we're dealing with normal sequences in this paper. So what does it mean for a sequence to be normal? Well, a sequence S is normal in base K. So that's if S was made from an alphabet of K characters. If for every string X of length N, X occurs as a substring in S with asymptotic frequency K to the minus N. So in our binary case, S would be normal if, as we take longer and longer prefixes, 0 and 1 both appear half the time. Any string of length 2, they all appear a quarter of the time as we take longer and longer prefixes. And like any string of length 3 occurs 1/8 of the time, and so on. So, simple example of normal sequences. So in base 10, one example is just to list all the positive integers in order. So 1, 2, 3, 4, 5, and so on. Another cool example would be if you list all the primes in order. That's another normal sequence in base 10. So why are we interested in normal sequences? Well, in many finite state based complexity notions, normal sequences have maximal complexity. And so in a sense, normal sequences are the quote unquote finite state random sequences. So for example, if your complexity was based on how compressible are prefixes of the sequence based on a finite state compressor, a famous result is that a sequence is normal if and only if, for all information lossless finite state compressors, all but finitely many of its prefixes are incompressible. So if you take any finite state compressor that's lossless, so this is just a finite state machine with inputs and outputs, and if you look at any old prefix, for when the prefix is long enough, the ratio of the output over the length of the original input, it's always going to be bigger than or equal to 1 minus epsilon, where epsilon can be made arbitrarily small. Okay, this is also true if your finite state compressor has access to a counter, or even if your compressor is allowed to move in 2 directions. So it's not just a one-way finite state machine, it's a two-way finite state machine. This is also true. So again, then the question we'll ask is, since automatic complexity is a finite state based notion, must normal sequences have maximal automatic complexity, i.e. is the lower automatic complexity ratio always equal to 1 for every normal sequence? Is this true? Well, intuitively, it probably isn't. So you may even think to yourself, well, it's probably not. And why is this the case intuitively? Well, in a sense, automatic complexity it's more of a combinatorial type measurement rather than an information content measurement. So like by that, what do I mean? Well, in like an information content type measurement, we would like there to be roughly 2n objects to have complexity equal to n. While in this case here for automatic complexity, as we've already seen, there are infinitely many strings with an automatic complexity equal to 2, as we saw by the string of just zeros example. So then I guess the question is, how low can it actually go? How low can these ratios go? Okay, so in the paper we built some sequences and examined this, and the building blocks of all of our normal sequences are de Bruijn strings. So what are these? Well, a binary de Bruijn string of order m is just a string of length 2 to the m that, when viewed cyclically, contains every string of length m as a substring exactly once. So for example, this here is a de Bruijn string of order 3. And if you just cycle through it, you'll see that it contains all strings of length 3. So you start off with 0, 0, 0, then you see 0, 0, 1, then 0, 1, 0, then 1, 0, 1. Keep cycling through, and eventually cycling back to the beginning when you need to, and eventually you'll see that all 8 strings of length 3 are a substring. Okay, so our first result uses the following theorem, which basically provides an easy way to construct normal sequences. And it says that for a function f over the positive integers that's increasing and that satisfies the condition that f of n is bigger than or equal to n to the n for all n, then if you have a sequence that's formed by taking d1 concatenated with itself f1 times, followed by d2 concatenated with itself f of 2 times, and so on, where each dn is a de Bruijn string of order n, the sequence here you build will be normal. So this provides us an easy way to build normal sequences. So again, the key idea is just concatenate repetition of de Bruijn strings of increasing order, and if you have enough repetitions, you're going to get normalcy. Using this technique, we were able to build a normal sequence T such that if you looked at the automatic complexity ratio of infinitely many of its prefixes, the ratio gets arbitrarily close to 0. And what we were also able to show was that the ratio was also bounded above by a half. Okay. So sketch of the proof. For each I, we let di be the Brownian string of order I, such that if I is even, di begins with a 0, and if I is odd, it begins with a 1. And then we construct our sequence T in zones T1, T2, and so on, where each zone Ti is going to be a De Broglie string of order I concatenated with itself f of I times, such that f of 1 is equal to 2, and for all j bigger than 2, f of j is going to equal to the length of all the previous zones combined. So as you can see, the length of these zones grows pretty fast. And by the previous theorem, t is going to be normal. So let's calculate the automatic complexity of this sequence. So we'll take an arbitrary prefix x such that the largest complete zone that's a substring of x is tj, and then w here is just going to be a prefix of the zone tj plus 1. And again, because the length of tj is so much bigger than the length of zones t1 to tj minus 1 combined, tj is going to dominate our calculations, and it's going to be the most important one when we come to creating a DFA that uniquely accepts x, as in x is the only string of its length that's accepted. And the way we'll do this is we will essentially just create a DFA that has a loop for dj, and this loop means we can decrease the number of states that are needed. So the DFA looks something like this. So we'll read zones T1 to Tj minus 1 bit by bit, have a state for each bit. And then we'll have a loop that reads the string dj. So essentially this is going to look like this. So we have 2j states up along here, and so on and so forth. And we traverse this loop f of j times. And when we've finished traversing that loop f of j times, we read w until we get to our accepting state over here. And the way our DFA is constructed, x is the only string of its length that is accepted. So this DFA gives us an upper bound for its automatic complexity. W short means that this ratio approaches 0, it can get arbitrarily close to 0. And this ratio will obviously get longer as w increases its length. However, at some point w is long enough where instead of looping on dj, it instead eventually is more advantageous for us to have a loop for dj plus 1 instead. And at this point, the ratio is approximately equal to a half. So this gives us what we state in the theorem, that it is 0 and that st, the upper bound, is less than or equal to a half. So that's kind of the rough idea of the proof. The second thing we examine in the paper is Champernowne sequences, and these are a certain subset of normal sequences that have a restricted construction. So to make these, what you have to do is concatenate all strings of length 1 exactly once, followed by all strings of length 2 exactly once, and so on and so forth. And you might wonder if, with this restricted construction, must Champernowne sequences have maximal automatic complexity? So when we discuss these types of sequences, we'll always break them into different zones, C1, C2, and C3, and so on, where Ci is going to be a concatenation of all strings of length I exactly once. So that means that the length of Ci has length 2 to the I, because there's 2i strings of length I, times I. So for example, here at the bottom, this is a perfectly acceptable construction of C1. Similarly, you could say C1 is 1, 0 either. There's different possibilities. It doesn't necessarily have to be in lexicographic order. This here is perfectly acceptable for C2, and then this here is perfectly acceptable for C3, and so on. So what we were able to show in the paper was that there exists a Champernowne sequence such that the upper bound ratio is less than or equal to 2/3. So again, it's less than 1. So how did we do this? Well, to make C, we used a construction of Pearson shields from the year 2000. And the way it works is for each j, we let dj be the Brownian string of order j with prefix 0j and suffix 1j. And what we do is essentially to make cj, we cycle through dj in windows of size j, printing the string we see and performing shifts when necessary. So what do I mean by that? Well, to make C3, for example, take your De Bruyne string of order 3 and look at the first window of size 3, which is 3 zeros. The next window is 101, the next window is 110, so on and so forth, cycling through in windows of size 3, and eventually all 8 strings will have been written. And so C3 then is just a case of concatenating all 8 of these strings together. C4, same idea, start with your 4 zeros, then look at the next window, the next window, and the next window. But then we have a problem because eventually we see the window of 4 zeros again. And if we were to write 0, 0, 0, 0, we'd have another issue because chamfer-node sequences, if you remember the way we built them, we can only list each string once. So this is a problem. So what we do is we take the first 0 and stick it at the end of the string. So essentially we've shifted the string cyclically to the left by 1 bit. And this here, this kind of becomes our new base string, if you want to call it that. This is our new kind of base string. And so the first window we see here is 0, 0, 0, 1. And then we see 0, 0, 1, 1. And again, we just continue this process of moving in windows of size 4, performing shifts when necessary. So at the end, C4 will look something like this. So just concatenate these 4 rows together. So like this will be concatenated with here, this will be concatenated with here, and so on. And these indents here are just to indicate kind of when a shift occurred. So you can hopefully clearly see there's lots of repetitions going on here. Repetitions mean loops, which we can use to minimize the number of states we need. C5 looks like this, again, lots of repetition. And C6 looks like this. So you can kind of spot here at the side that we were able to list out half of the strings of length 6 before we had to do a shift here to get the other half of the strings of length 6. Okay, so let's calculate the automatic complexity. Well, we let x be such that Cn plus 1 is going to be the largest complete zone, that's a substring of x, and w is going to be a prefix of the zone Cn plus 2. So the way we'll do it is we'll read C1 to Cn minus 1 bit by bit, so having a state for each of those bits. We'll use 2 loops. We'll have a loop for zone Cn, and we'll have a loop that reads zone Cn plus 1, and then we'll read w bit by bit by bit. And looping on these 2 largest zones, again, means we can reduce the number of states we need. And the fact is, one of these loops is going to have odd length, and one of these loops is going to have even length. And that ensures that there's only x, that ensures that x will be the only string of length x that's accepted. So for example, to read x, maybe you have to traverse the first loop 8 times and the second loop 9 times. Well, maybe it's impossible then for us to traverse the first loop, let's say 9 times, and the second loop 8 times, and have a second string w such that the length of w equals to the length of x. That's also accepted. So this is impossible. The fact that one of these loops has odd length and the other has even length, this ensures that x is the only string of its length that's accepted. So it can be used to estimate the automatic complexity. So if we were to do C4, our loop would be these bits shaded here in blue. So you can see there's repetition going on, which we can exploit. So this loop here has odd length. We just make a note of that. C5 would look like this. So the loop would be these bits again shaded in blue, and you can see there's like lots of repetition. You can see this loop has even length. And C6, because of the shift here, our loop has this length. So our loop is much bigger compared to the other loops. So for example, in C6, the number of states we'll need for the loop is going to roughly equal to half the length of C6. While if we just go back briefly, the number of states we needed for C5 was roughly a fifth of the length of the string. And similarly, C4, it's roughly a quarter number of states is needed compared to the length. So C6 is kind of bad for us because we need a lot of states for it. Okay, so if n was a power of 2, this is the style of DFA we would use. This would be the DFA we use in the paper to examine its automatic complexity. So here dj is just split into these three substrings 0j, 1, vj. And so what you do is you read up to zone cn minus 1 bit by bit by bit, and then you read the first n bits of dn. Then you would traverse this loop n times, and then once you've finished that, you've fully read cn. Then you read the first n plus 1 bits of dn plus 1, and then you would traverse this loop n plus 1 times. And then depending on the length of w, you would traverse along here until you reach the final state. And if w is short, it's possible that maybe one of the states along here could also potentially be the accepting state, depending on what the length of w is. But the fact that this loop here has odd length and this loop here has even length, this ensures that x is the only string of its length that is accepted. So for example, if n was 4, this would be the loop, and if n, then that means n plus 1 is 5, and this is the loop. Worst case scenario, n is even but not a power of 2. So for example, C6, as I said earlier, because 6 is 2 times 3, and we saw the size of its loop. Well then, the DFA we use looks something like this. So as you can see here, this loop is going to be big compared to the other cases, which again increases the number of states we use. So as I said, the first loop may have up to 2 to the n minus 1 times n minus 1 stage, which is again roughly equal to half the length of Cn. When this is the case, the point at which, instead of looping for Cn, and it becomes more beneficial to loop for Cn plus 2 when w is long enough, the point at which this occurs, this ratio is just less than 2/3 plus epsilon, where epsilon gets arbitrarily small as n gets bigger and bigger and bigger. So this gives us that S of C is less than or equal to 2/3. So the paper itself deals with all the different cases and the calculations that we use to come up with this. So it contains the different cases and the DFAs for it. So I guess then some future questions. Can this bound be tightened? So we make no claims in the paper saying that this bound is tight. One way it might be improved upon is, for example, when n is even but not a power of 2, we assume it's equal to 2 times p, where p is odd. And then in later calculations, we also assume that n plus 2 is also of the form 2 times q, where q is odd. But this obviously cannot be true, because one of these has to be a multiple of 4. So maybe taking this into account in the calculations, this number here can be improved upon. So that's maybe one potential path. In the proof, we only use 2 loops in the DFAs we construct. Can this number be increased? But I guess the problem is, the more loops you introduce, the more possibilities of introducing another string whose length is equal to x, the prefix we're examining, that is also accepted, which we don't want to have happening. In the paper, we include one example where 4 loops are used, but again, we just point it out as an example. We don't do any further investigation into it. What about the lower bound? Well, we don't really say much about that in the paper either. The best we can say, or the best we state, is that it is at most a quarter. So future area of work could be trying to figure out, for example, is it strictly bigger than an eighth, for example? Is it strictly bigger than 0, for example? Is it equal to 0, for example? I don't know. We haven't explored. So maybe there's an argument from number theory, like involving Diophantine equations or prime numbers, that is staring us right in the face, that I just haven't spotted yet. So if anyone has any ideas or insights that could potentially help solve this, I'd love to hear from you. So thank you then, everybody. I hope you enjoyed the talk. Bye bye.